backseat for a getaway, car top down.
Hi everyone. So today I and my friend will discuss about radiation. I guess most of us does not know what is radiation. So today we are here to tell you about radiation. Okay. So far we have learned and considered about conduction and convection modes of heat transfer, right? So now we are turn our attention to the third mechanism of heat transfer, radiation, which is characteristically different from the other two. Okay, in that sense, radiation transfer does not require any material medium, any presence material medium to take place. It also can occur in solid as well as liquid and gases. Other than that, radiation transfer can occur between two bodies that's separated by a medium colder than both. Okay guys, radiation propagates in the form of electromagnetic wave. The frequency and wavelength in the electromagnetic wave in that medium are related by this equation. Okay, where c is the speed of propagation in that medium. Okay, next, all matter whose temperature is above absolute zero continuously emits thermal radiation. It is as a result of vibrational and rotational of motion of molecules, atoms, and electrons of substances. Okay, there's a lot of example radiation such as ultraviolet, X-ray, radio, microwave, and many more. Other than that, everything around us also can emit thermal radiation such as people, furniture, walls, and plants. Also, in thermal radiation, temperature is a measure of the strength of these activities at the microscopic level. In other words, the rate of thermal radiation emission increases with increasing temperature.
Okay, first is about black body radiation. Black body radiation can be defined as perfect emitter, diffuse emitter, and also perfect absorber. A black body is an ideal radiator that absorbs all incident radiation regardless of wavelength and direction. You can see the diagram figure 11.7 at the slide. There are differences between black body surface and real body surface. Is black body emissive power. Black body emissive power is the radiation emitted by a black body per unit time and per unit surface area. This is the basic black body equation. EB equal to sigma T to the power of 4. EB is total black body radiation energy, while sigma is the Stefan-Boltzmann constant. You can see the value. So T is temperature, which is absolute temperature. Next is spectral black body emissive power. Spectral black body emissive power is the amount of radiation energy emitted by a black body per unit surface area and per unit wavelength about the wavelength. So you can see the formula on the slide. This formula is only valid for surface in a vacuum or a gas. So the C1, the value for C1 is given, same to the C2 and also K. K is the Boltzmann constant. As you can see from the graph, it has curve. So this is the little explanation. As the temperature increases, the peak of the curve in the figure shifts towards shorter wavelength. The wavelength at which the peak occurs for a specified temperature is given by Wien's displacement law as it shown below. So next is total black body emissive power. Total energy is integral over all wavelength. On the chart, an area under the curve for a given temperature represents the total radiation energy emitted by a black body at that temperature. So this is the integral equation. Next is black body radiation function. Black body radiation function is the fraction of radiation emitted from a black body at temperature T in the wavelength band from 0 to lambda, as you can see in the graphical representation of fraction of radiation emitted here. Next is diffuse gray surfaces. Based on Kirchhoff's law, the absorptivity of a non-black surface is always equal to emissivity of the same surface when the surface is in thermal equilibrium with the radiation that pings on it. So this is the thermal equilibrium. To a lesser degree of certainty, we can write a more restrictive form of Kirchhoff's law for diffuse gray surfaces, where emissivity equal to absorptivity. For Kirchhoff's law requires that the radiant source and the surface be in thermal equilibrium. It is seldom the case. The law can still be used, but you should proceed with equation with caution when the two temperatures differ by more than 100 K. And lastly is the absorptivity, reflectivity, and transmissivity. When radiation strikes a surface, part of it is absorbed, part of it is reflected, and the remaining part, if any, is transmitted. So this is the equation, and you can see the figure here. That's all from me. Thank you.
I will start my presentation with the view factor. Radiation heat exchanger between surface depends on the orientation of the surface relative to each other. Dependence of orientation is accounted by the view factor. So, view factor purely geometric quantity and is independent of the surface properties and temperature, which is the view factor only depends on the geometrical shape of an object. The surface properties and the temperature are not the factor that affect the view factor. There are two types of view factor. The first one is diffuse view factor and the second one is specular view factor. The diffuse view factor is a factor based on assumption that the surface are diffuse emitters and diffuse reflector. But specular view factor is an assumption that surface are diffuse emitters but specular reflector. From you can see on the slide, there is a point source and how the radiation effect on the geometric surface of an object. We continue to how to calculate the view factor. For example, you can see from the slide there is two objects, two surface, from surface 1 to surface 2. We can calculate the view factor from radiation from surface 1 that strike to the surface 2 directly. We calculate from the formula F12. But to calculate the radiation of surface 2, we can using formula F2A, which is the surface that lift from surface 2 and towards to the surface of surface 1. We continue to radiation exchange between the surface. There is two type of situation where how it happen in the surface. The first one is black surface. The black surface, from what my understanding, it is a process that radiation happen only directly from one surface directly to the another surface, which is there is no other reflection occur during the process. So this can be calculated by using radiation from surface 1 to surface 2 minus the radiation from surface 2 to surface 1. You can see from the slide. Next, we go to the second type of surface, which is grey or diffuse surface. This radiation from one sources, for example, hit one surface and reflect, but compared to black surface, only one reflect radiation, but for diffuse or grey surface, there is consists of two others radiation occur. The first one is reflected radiation, and the second one is emitted radiation. You can see from the slide there is two calculation occur for this type of surface. We continue to the radiation of resistant network. Why it is called as resistant network? This is because the concept of the radiation is the Ohm's law, the electrical formula, Ohm's law concept is being applied to the to understand the radiation concept. So by using this Ohm's law, using resistance network, it is used a schematic diagram to show how the process take place. So from slide you can see there is three situation occur. You can see from the picture at the slide. The first one is radiation from surface or another from surface to another point. So there is only one direction. But you can see from the picture in the middle, there is various resistance occur along the surface until there is, for example, there is two surface. So the radiation occur, the resistance network occur have various type. But the last one, where this resistance network occur, you can see from the picture from the slide on the right side, you can see that there is various surface. So the radiation, by applying Ohm's law, we can understand the schematic diagram. So the resistance network actually is the way how we interpret the situation occur into a schematic diagram. That's all for me. Thank you.